statistical test that could be performed on PSPP. And the topic for today's session is comparison of means. Why it is called as comparison of means? Because in these tests, we basically compare the two means, that is the population mean or the population mean and the sample mean. So I hope this slide is visible to you clearly. So the
Yes, sir.
first test of comparison of means is one sample t-test. This one sample t-test determines whether the sample mean is statistically different from a known or hypothesized population mean or not. So we have two mean, a hypothesized population mean and a calculated mean. And we see that this calculated mean is also called as sample mean. And we see that whether there exists a significant difference between the two populations or not. So normally we use this test uh, when we want to know that whether our sample has been drawn from the same population, whether the sample characteristic are as same as the population or not. This is a two-tailed test. Why two-tailed test? Because there is a hypothesized mean known as population mean, and we test that whether our sample mean or calculated mean is less than this hypothesized mean or greater than this hypothesized mean. So there is a midpoint population mean, and when we calculate the sample mean, we see that whether it is less or greater than that. That's why it's called a two-tailed test, and this is a parametric test. Means it follows the assumptions of normality. So this test is also known as single sample t-test, and the variable used in this test is known as test variable. You have only one variable. There is nothing called dependent variable or independent variable. You have one variable known as test variable, and you check whether the mean of this variable is greater than or smaller than your hypothesized population mean or not. So in a one sample t-test, this test variable is compared against the test value, and that test value is your hypothesized population mean. Okay. Data requirements. Before coming to the data requirements, I'll just discuss about what are the common uses of this one sample t-test. So normally this one sample t-test is used to test the statistical difference between the sample mean and the population mean. And it is also used to measure the statistical difference between the sample mean of the test variable and chance probability of occurrence, and also used to measure the difference between a change score and zero. Now, the data requirements for doing this test, because you need to understand for every test there are some requirements of data that needs to be fulfilled, then only you can apply that test. So your data must meet the following requirements for conducting a one sample t-test. Means the test variable that you are trying to measure, it should be taken on a continuous scale or a metric scale, which is either an interval or a ratio scale. Then the scores that you have measured on the test variable are independent of each other. Means one score should not be affecting the another score. There should be independence of observations. Like weight of 10 people. Weight of one person cannot affect or cannot lead to the weight of another 9 people. So if we are taking the weight, height, or any of the parameters, all these observations are independent of each other. Means there is no relationship between the scores and the test variable. Because if there is some relationship between the score that you are taking and the test variable, then the p value, that is the probability of occurrence value, will be inaccurate. Data should be taken randomly, means you can take means the data you have collected, that should be the sample that you have collected, or the sample you have chosen for data collection, that should be taken through probability based sampling or random sampling. Data should follow the assumption of normality, that is normally distributed. It should not be, sometimes it happens that data is not much normally distributed, then also you can conduct this test, but always take care that it is not heavily skewed, not heavily skewed towards one side. Because it is the second point, that is among moderate or large samples, a violation of normality may lead to accurate p-values. But if it's a small sample size and the data is very highly skewed, then that's a problem. There should be homogeneity of variances. So variances should be approximately equal in both the sample and the population, and no outliers. Basically, outliers are the extreme values, the minima extreme or the maximum extreme. Let's say in one class there are 50 students whose age ranges from 20 to 25. Normally, one or two students are of the age of, let's say, 35 plus. This is the extreme value, outlier. Or one of the two students are of the age 15 to 16. Then again, this is an outlier. So outlier is a small proportion of the sample that is either which is very much deviated from your normal observations. Means it's either very minimum extremity, it will follow either the minimum extremity or maximum extremity. So since it is a mean comparison, so outliers could affect your mean values significantly, so there should not be any outliers. Now hypotheses that we formulate in case of one sample t-test. So basically we formulate the null and the alternate hypothesis. So the alternate hypothesis is mu is equal to x bar. Actually, this is x bar. Kindly read it as x bar, which means that the sample mean, that is the x bar, is equal to the proposed or the hypothesized population mean mu. So here mu is equal to your population mean and x bar is equal to your sample mean. This shows that there is no significant, normally we write, in case of one sample t-test, the null hypothesis, we write that there is no significant difference between two variables or two means. So here if you are saying that mu is equal to x bar, that is the population mean is equal to sample mean, in fact we are saying there is no significant difference between the two. In alternate hypothesis, we write that there is a significant difference between both the values, between the population mean and the sample mean. That is represented by mu is not equal to x bar. So if mu is not equal to x bar, what will happen? There will exist a significant difference between the two means, that is the sample mean and the population mean. So we have taken two means, mu and x bar, where mu is the constant proposed for the population mean and x bar is the sample mean. Now we have a problem statement and we'll solve this problem statement through our data set. So according to this data has been taken from the Center for Disease Control. I have already shared this data with you. I hope you are having this data set. Along with the data set, I have also given a PDF file of data code book so that you understand that what basically this data set is talking about. So according to the Center of Disease Control, the mean height of the adult age 20 and older is about 66.5 inches, which is Again, if we calculate among males and females, so the average is 69.3 inches for males and 63.8 inches for females, and total mean age of adult is 20 or above is 66.5 inches. Now we have to test that if the mean height of our sample that we have taken, because CDC says that in the overall population, the adult who are above the age of 20, their average height is 66.5 inches. Now we have measured uh, the height in a sample, and we want to check that whether the mean height of our sample data is significantly different from this 66.5 or is equal to this. So this could be tested through one sample t-test. In this case, our null and the alternate hypothesis will be, the null hypothesis is x bar height, which is this height of the sample, is equal to mu height. And here mu height is already given, 66.5. So ultimately we are saying that the mean height of the sample is equal to 66.5. In alternate hypothesis, we are saying that the mean height of the sample is not equal to the mu height or population, the height of the population. That is the mean height of, and height of the population on an average is given 66.5 inches. So we are basically saying that the mean height of the sample is not equal to 66.5. In wording, we can say like this, that there exists no significant difference between the population mean and the sample mean, and there exists a significant difference between the population mean and the sample mean, where your population mean is equal to 66.5 inches. Now let's test this, whether this stands true or not. So I hope every one of you have access to this data set, sample data set. It would be better that if you practice with me, that would be better. So now this is the environment that we have got. Now let's import the data. So I have saved in F drive, and it's here. Sample data set. So all cases I want to import, then select next. Now I would like to, this one is my first data set, first line. So I will select this first line, and I will select the line above the selected line contains variable name. All these are variable names. Then moving on to the next, I can see this will be the layout of the data. Next, and apply. Now I have the data set with me. This is the variable view of the data set, and this is the data view I am having. So what I wanted to check, that whether my sample mean is different from the population mean or not. And for that I have framed two hypotheses also. Before doing this test, let's check the nature of this data set through the descriptives. So analyze descriptive statistics and go to descriptives, and it was, we have taken height, mean, standard deviation, minimum, maximum. You can check. Now here my output says that the minimum height in my population is 55 and the maximum is 84. And the mean height in my population comes out to be 68.03 and the standard deviation of 5.33. Now, if I want to plot it on a graph for having more meaningful insights, I can plot it on a histogram also. And we can do that through graphs, histogram, and take the height. Okay. Now again check your data output. Now here you can see that your highest height that you have got here is somewhere 84.4, nearby 90. Sorry, this is the frequency. Uh, you have got the height around ranging from around 55 to somewhere 84, like this. The data represents this, and frequency you can calculate how many people. Just to have a look, uh, just to the preliminaries of the test.
Sir, sorry to interrupt.
Yes.
Uh, Sir, somewhere I have missed while importing the file. At this, I'm just getting this. I'm not getting height and all. I'm getting variable 01, variable 02 when I imported the file.
Okay. Can you please do along with me? I am just repeating it
Yeah,
again.
yeah, 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 fine.
I am opening the software. Please just repeat along with me.
Yeah.
So hands-on means that you have to practice along with me, because if you just listen to the lectures, I don't feel it's worth. So better listen it on your mobile phone and practice on your laptop.
Then we
Yes.
will be what we have to do. Sometimes it happens that we have to just log in with two devices. Is it okay with you?
Yeah, it's okay. It's not a problem to me. Not a
Then it's
problem.
okay.
You can.
Fine.
My overall agenda is to create a learning environment. That's it.
So
So are you
nice.
getting this?
Yeah, I'm here. File and
Simply go to file, import data,
right.
go to your file location.
Hmm.
In my case, my file location might be different from yours. So
Hmm.
this sample dataset.csv, have you found this file?
Yes, yes, yes.
Click on next.
Click on next, all cases.
Again, click on next.
Hold a minute.
Are you getting this window?
Just a minute, sir. All cases, next. Yes, sir. At this window,
Select the
something
second line,
went
because
wrong.
this from here, this line your data will start. So select the second line,
Select the second line.
and below select this line above selected line contain variable name.
Line above. Okay, this I missed. Fine.
Select next.
Yes.
You will find this layout. Now you can see that how your data is arranged.
Right.
File
Yes.
in and apply.
Okay. Thank you,
Now,
sir.
now hopefully you have got data like this.
Yes, yes, yes.
Okay. So
Thank you.
preliminaries we have tested. Now let's check for one sample t-test or hypothesis. Let's
Right.
test. So go to
Descriptive.
analyze, compare means, and one sample t-test. Now we wanted to do this for height. So our test variable is height. What would be our test value?
Height. Wait. Height.
So height we have taken as the test variable. What will be our test value?
You. What was the hypothesis?
What we wanted to measure
So
in this
that
case?
is mean value, I think 66 point something.
Exactly, that will be 66.5. The mean value means that is the value of the hypothesized mean, the population mean, 66.5. We wanted to test whether our sample size is below this or above this. Now go to options. By default, 95% confidence interval is there. 5% confidence level is there. Exclude cases, because sometimes there might be missing values, so we want to neglect those missing values. This is the data set of 435. Some are missing. So exclude cases, analysis by analysis, select this, continue. Okay. Now go to the output. Now in the output, you might be seeing that you have got the one sample statistics, the mean value 68.3, height of your population, the mean height of your population. And you can compare when we have done that analysis, the basic descriptives, the mean value was this much only, the standard deviation was 5.33. We have got. Now look for the table. And how come we are getting now? Our t value is 5.81. Degree of freedom is 407 because in one sample t test, degree of freedom is equal to n minus 1. Number of observations minus 1. We had total number of 435 observations, but why 408 has been calculated? Because 27 were missing, and already we have defined that leave those missing, exclude the cases by step. So degree of freedom, at the degree of freedom 407, the value of t comes to be 5.81 and the p value is equal to 0.000. This is less than 0.05. So null hypothesis is
Accepted.
rejected. Somewhere write it down. This is the thumb rule. If p is less than alpha, where alpha is your significance level, p is less than alpha, reject null hypothesis. So in this case, your p 0.000 is less than alpha. From where this alpha is coming, that is your confidence level. You have the confidence interval of 95%, so you are leaving a chance of error, margin of error as 5%, which you just write into numbers, it will be 0.05. So if it is less than 0.05, null hypothesis is rejected. And from where are you getting this t value? It's simple. T value is equal to nothing but a mean difference divided by standard error mean. You can simply see it here. So if I divide the mean difference 1.53 by standard error mean 0.26, I'll get this 5.88, like this, nearby somewhere 5.81, 5.88. This will be the t value that I'm getting. So now what can we say? Null hypothesis is rejected. Fine. Anything else we can write about this?
There is a
So
significant difference, sir. Yes.
only you can write there is a significant difference. Anything else that you can write apart from this? Because simply writing p is less than alpha, reject null hypothesis, that won't work. First thing, the proper style of reporting a t test is t at the degree of freedom, sorry, it will be small t, degree of freedom was 407 is equal to 5.81, mean is equal to, what was our mean value? 68.03, 68.03, standard deviation is equal to, because you have to tell about the deviations from the your mean value. So that will come into the form of standard deviation 5.33. 5.33. At this level, p is less than 0.05. That's why null hypothesis is rejected, which shows there is a significant difference between the population height and the sample height, where population height was found out to be 66.5 inches on an average. In our collected sample, the height was found to be 68.03 on an average. You have to write, report all these things. Right? And if you calculate, it will give you this mean difference. I think it should be like this. Let's check. 68.03 68.03 minus 66.5, 1.53. This is the mean difference that is coming between your population mean height and the sample mean height. So your sample mean height is greater than 1.53 inches as compared to the population mean. This entire thing you have to report, because simply writing P is less than alpha, so null hypothesis is rejected. This won't yield any information for the reader until and unless you tell that what was your case, how much height you have got. Am I clear on this? Yes, should we move forward?
Yes, sir.
Okay.
Yes.
So this is one sample t-test, and reporting is important in almost all the tests. You have to see that which of the which of the statistics you have to report. Now, coming to two sample test. In our previous case, we didn't had any dependent variable or independent variable. We only had a test variable. And that test variable means was only a mean value we wanted to test
मेरे पास नहीं है
how much it is deviating from our population. That's it. But what if I want to know if I have a dependent variable and independent variable, or I have two means where one of the mean value or one of the variable is divided into two groups. This is a case of two sample t-test. Further means two groups, that is k equal to 2. Is this decision tree visible to you all? Or let me enlarge it.
Yes.
Now, so if you have the case where you have a dependent variable and independent variable, where your independent, because this is a case of univariate analysis, you will be having only one dependent variable and only one independent variable. Don't confuse that here you have two independent variable. You have only one independent variable where your independent variable is divided into two categories. This will be a case of two sample test. Now further, if your dependent variable groups, if your IDV groups, they are mutually exclusive of each other. They are totally independent of each other. Means characteristic of one group is quite different from the characteristic of the another group. Then it will be case of independent sample t-test. If your group is divided as such that both the groups are not mutually exclusive of each other, then, or somewhere they are related, then you will go for dependent sample t-test or paired t-test. Now for applying independent sample t-test, a few of the assumptions has to be met. If the data is taken on a categorical scale, that is either ordinal or nominal, directly move to the non-parametric equivalent of the independent test, that is the Mann-Whitney test, U test. However, if your data is metric in nature, that is continuous, taken on a continuous scale, that is interval or ratio, then further check whether it follows the distribution normality distribution or not. So normality could be checked either by Shapiro-Wilk test or by one sample case. Shapiro-Wilk test is stronger statistics than one sample case or one sample Kolmogorov-Smirnov. The only problem with Shapiro-Wilk is that it is not suitable for large sample sizes. If you have large sample sizes, go for this one sample case. If your data does not passes this normality distribution, again move to the Mann-Whitney test because you have to move on to the non-parametric equivalent of the test. Why I have moved directly in case of categorical data? Uh, I said that if it is a categorical data, directly move on to Mann-Whitney test or non-parametric test, because if you are taking a categorical data, it won't be normally distributed. You are taking, let's say, two categories here. If you are taking data on categories like age divided into categories, either the respondent will tend to skew towards one age, either they will be grouped into one group or another category. So it won't be normally distributed. So directly go for Mann-Whitney test. However, if it's a metric data, go for the normal distribution. If it passes the normality test, then go for Levin's test for homogeneity of variances. However, if all cases are successfully met and Levin's test of homogeneity of variances is not met, then nothing to worry about. Reason being, when you are doing this independent t-test, it yields you two values. One case is when equal variances are assumed, and another case is when equal variances are not assumed. So if it does not passes the Levin's test of homogeneity of variances, still the case is like that your data is taken on a metric scale, the groups are mutually exclusive of each other, then you can proceed for independent t-test, no problem in that. Somewhere the p-value would be disturbed, but not much if you have greater sample sizes. So you can directly move, no issue with that. One example could be, let's say, I want to measure emotional intelligence among males and females. Now I have two categories of my independent variable which are affecting the dependent variable, because emotional intelligence I want to see in my sample. And I want to see how across the two categories this emotional intelligence varies. Where males, the characteristic of male is quite different from the characteristic of female. However, if the same case is, I have not divided my category in male and female. Now my category is, I want to test the emotional intelligence among my samples, let's say at their teenage and at their younger age, or when they were teens and when they have moved to adult age category over a period of time. Now here my category is two. Same sample when they were teenagers, the same sample when they have moved on to the adults. People remain the same. Only categories, these two categories, they cannot be mutually exclusive of each other, because it could not be the case that emotional intelligence will change drastically, or anything will change drastically from teenager to younger age. No, some of the characteristic will remain. Only few will change on the basis of experiences. Let's make it more simple. I want to make the tea. चाय बनानी है मुझको. Now the ingredient of tea is sugar, tea leaves, water, milk, And to add to its flavor, I have added cardamom and ginger. If the case is I want to test the effect of flavoring agents on the flavor of the tea, where my flavoring agent is again divided into two categories, cardamom and ginger. I'm treating not treating them as two different variables. They are one variable known as in flavoring agents. And these flavoring agents divided into two categories, ginger and cardamom. Now, if I want to see this, the characteristic of ginger and cardamom are not the same. They are mutually exclusive of each other. They will affect the flavor in a different way, or the taste in a different way. That will be the case of independent sample test. Now, second case is I want to check the effect of sugar on the taste of tea after adding 1 teaspoonful of sugar and after adding 2 teaspoonful of sugar. Or simply effect of cardamom on the flavor of tea after adding 2 milligram of cardamom powder and after adding 3 milligram of cardamom powder. Cardamom powder is the same. Okay. Only it has been divided into two categories. When it was only 2 milligram, when it was only 3 milligrams. This will be the case of dependent t-test or pair t-test. So, if such is the case, and again you have taken data on a categorical scale, no need to further test it. Go to the non-parametric equivalent of the paired of the dependent t-test. The parametric is the pair t-test. Go for its non-parametric equivalent, Wilcoxon test. However, if the data is taken on a metric scale or a continuous scale, that is ordinal or interval or ratio, further check for its normal distribution. If it is normally distributed, fine, go for the pair t-test. If it is skewed, again move on to the non-parametric equivalent, that is the Wilcoxon test. I hope this concept is clear. Yes, audience.
Yes, audience. Yes, sir.
Now let's see. Okay, I have talked about two concepts, normal distribution. So this is the normal distribution curve, you can see. And second case is the homogeneity of variances. Suppose I have taken the two groups, male and female, and I want to test emotional intelligence among male and female. Now, among my population, if there are only 10 females and 100 males, can I test the emotional intelligence? Whatever the statistic I will be getting, that will be wrong because my sample, the characteristic is not proportionately distributed, not homogeneously distributed. There is a lot of heteroscedasticity. So you can just understand it by a simple concept. These both are normally distributed curve. While population 1, in case of population 1, you can see that it's very steep and very narrow. This is the case of heteroscedasticity. Whereas in this case, you can see that it is ranging from -6 to +6. Okay, you can say somewhere it is homogeneously distributed. The value that you are trying to test, the variable that you are trying to test, that is equally distributed among your groups. And because the groups are mutually exclusive of each other, so you have to check that whether your test variable or your independent variable that you want to test, the dependent variable that you want to test, whether that is equally distributed among among the two categories of your population or the sample or not. If that is not the case, again there will be problem. Now let's take the first case, independent t-test. So this independent sample t-test, already I've told, compares the mean of two independent groups in order to determine whether there is a statistical evidence that the associated population means are significantly different. The population means associated with these groups, whether they are significantly different or not. So I have group 1 and group 2. Whether the mean differs between the group 1 and group 2 or not, or it is same across both the groups. So if I want to check the emotional intelligence among male and female, I basically want to check whether emotional intelligence is equal between male and female both, or it is different in males as compared to females. That's where the comparison of means comes. This is again a parametric test, means normal distribution, continuous data, all these things taken on a continuous scale, metric data, all these assumptions are met. It is known as independent t-test, independent measure t-test, independent two-sample test, student t-test. It has different names. It is also known as uncorrelated score t-test, unpaired t-test, unrelated t-test. Okay. The variable that is used in this test are known as dependent variable or the test variable that you want to use, and the independent variable divided into groups, also known as grouping variable. The common uses of this independent t-test is to check the statistical difference between the means of two groups, statistical difference between the means of two interventions in case of experimental research design. Suppose if you are giving two different treatments known as which is known as intervention, you want to check whether there is a difference between these two interventions or not. Let's say two group of people suffering from COVID. One is given the let's say Covaxin, the indigenous vaccine made in India. Another is given the vaccine made by the Pfizer, and we want to check how these two results will vary. Then we have taken the vaccine, COVID vaccine itself, but again these COVID vaccines are of two different kinds. Pfizer has made a different kind of vaccine, Covaxin is a different kind of vaccine, and we want to test. So mostly in clinical researches, mostly in scientific research designs, we go for this independent t-test, and that's why when you have studied statistics at your basic level, then you might have heard student t-test being used in science a lot. So actually student t-test is nothing but independent t-test, which is used to check the measures or the scores or the statistical difference between the means of two interventions. And then it is also used to measure the statistical difference between the means of two scores. So the independent t-test can only measure the means for two groups. If you are having more than two groups, then you have to move on to ANOVA. Now the data requirements for independent t-test is your data must be taken on a continuous scale, that is the interval or ratio scale. Independent variable should be categorical in nature, means the test variable or the dependent variable should be continuous, whereas independent variable should be categorical or taken on a non-metric scale or categorical scale like nominal or ordinal. Then cases that have values on both the dependent and independent variables, the data should be divided like such. Your sample or group should be independent, means there should be independence in the observations. All the observations should be mutually exclusive of each other. Because if this violation will be there will be an accurate p-value.
Sir, your voice is not properly audible.
My voice, is it breaking?
Yes, sir, please raise your voice.
Okay. Is it audible now?
yes, sir. Now it is audible. Sometimes it's very slow. मतलब I'm unable to audible and understand what you are saying.
No, then tell me in between. Actually, I am speaking at the same pitch. Sometimes network disruptions are there. So again, I repeat. So data requirements are that uh, your data must be taken on a continuous scale. The dependent variable basically should be taken on a continuous scale. Independent should be categorical, that is taken on an ordinal or nominal scale. Your cases that you have taken, they should have values in both the dependent and independent variables. The observations should be independent of each other. One observation should not affect the another one. No group can influence the other group. Like this, they should be mutually exclusive, else there will be problem in the p-value. Then you draw the sample randomly. Data follows the normal distribution, and there should be homogeneity of variance and no outliers. Now the hypothesis that we frame in case of independent t-test, the null one and the alternate one. So the null hypothesis says that mu1 is equal to mu2, means the two population means are equal. Means there is no significant difference between both the population means. Means when you have taken the mean, you have taken two groups of independent variable, and when they are divided into your populations, one group is, the mean of one group is not having any significant difference from the another group. Whereas the null hypothesis alternate says mu1 is equal to mu2. Mu1 is not equal to mu2. That means there exists some significant difference between the two groups, the observation of the two groups, their mean values. Or you can write it in other words, simply just transpose it in mathematics. H naught is, that is your null hypothesis, says mu1 minus mu2 is equal to 0. Simply, there is no difference. Mu1 minus mu2 is equal to 0. That means there is no difference, or the difference between the two population mean is equal to 0. And mu1 minus mu2 is not equal to 0. That means the difference between the two population means is not 0. You can write either ways. Either you can write mu1 is equal to mu2 and mu1 is not equal to mu2, or simply you can write mu1 minus mu2 is equal to 0, or mu1 minus mu2 is not equal to 0, where mu1 and mu2 are the population means for the group 1 and group 2 respectively. Then you have, since a very important statistic in case of this independent t-test is that you have two different groups and your dependent variable is distributed among those groups, so you have to check whether it is homogeneously distributed or not. For that you have the Levin's test for equality of variances. For that also you will make the hypothesis. So your hypothesis will tell you that sigma 1 square minus sigma 2 square is equal to 0. That means the population variances of group 1 and group 2 are equal, means equal variances assumed. This is the first case, equal variances assumed. And sigma 1 square minus sigma 2 square is not equal to 0. That is the population variances of group 1 and group 2 are not equal, means equal variances not assumed. Till here I am clear? Am I clear on this point?
Yes, sir. Clear. No problem.
So
Yes,
when
sir.
you write the hypothesis in case of independent t-test, not only this hypothesis you have to write, you have to also write the hypothesis of this also. That whether the Levin's test of equality of variances is there or not, whether the equal variances is assumed or equal variances is not assumed. Even you have to write this hypothesis and test this. Now, the data setup for this type of statistical analysis is your data should include two variables that will be used in the analysis. The independent variables should be categorical and include exactly two groups, neither less than that. If less than that, it won't be the case of uh, two sample test, and it should not be more than two also, because this is the limitation of independent t-test. It's only a two group test. Now our problem statement. Let's look at our data set. In our data set, students reported their typical time to run a mile. Simply look at this data. Mile mean DOR, the time taken to run a mile, right? This is the time in minutes which was taken by our students to run a mile. Where now this is the this is the ratio scale. Absolute metric data have been taken. And then our student groups are divided into two categories. Zero is equal to athlete, zero is equal to non-athlete and 1 is equal to athlete. So we will check the time taken by athletes versus non-athletes to run 1 mile distance, whether this is statistically significant or difference or not. Means we have to check the time taken by athletes versus non-athletes for 1 mile. Is this the same in both the cases or different? Are you getting the problem?
Yes, sir.
Okay. This is our problem statement. Now, the hypothesis for this example could be expressed as mu non-athlete, that is the mean score of the non-athletes, is different from the mean score of the athletes. Means score here means time taken to run 1 mile. Or mu non-athlete minus mu athlete is equal to 0. The difference of the means between the two is equal to 0, or there exists no statistical significant difference. See, why I'm saying every time significant difference, because it might be case sometimes very small differences may exist. But even if that is significant, that matters. Sometimes large differences may exist, but if it is not significant, it does not matter. So it's not about the difference, it's about the significant difference. Statistic that have some statistical significance. So in this case, our hypothesis either we can write like this, that there exists no difference between the time taken by athletes versus non-athletes to run a mile, and there exists a significant difference between time taken by athletes versus non-athletes to run a mile distance. Or mu non-athlete is equal to mu athlete, and mu athlete is not equal to mu athlete. Or mu non-athlete minus mu athlete is equal to 0, or mu non-athlete minus mu athlete is not equal to 0. So like this, you can frame your null and the alternate hypothesis, where mu athlete and mu non-athlete are the population means for athletes and non-athletes respectively. Now let's check this. Let's check this hypothesis in case of our data. So simply you have
सर, जब
to,
भी हम मीन वेरिएबल्स चेक करेंगे तो एक डिपेंडेंट और एक इंडिपेंडेंट वेरिएबल लेंगे ना अपनी स्टडी।
जी हेलो,
जब भी हम मीन डिफरेंस चेक करेंगे टी टेस्ट में तो एक डिपेंडेंट एक इंडिपेंडेंट वेरिएबल का करेंगे।
एकदम जी,
सॉरी सर।
हाँ एकदम करेंगे। तो यहाँ हम क्या कह रहे हैं कि जो दूरी है वो कम करने में, ठीक है, ये स्टेटस पे डिपेंड करता है कि नहीं, एथलीट्स वेयर स्टेटस इज डिवाइडेड इनटू एथलीट एंड नॉन एथलीट।
Hello, sorry for interruption.
Yeah.
Madam, actually in this, am I audible?
Yes, sir. Yes, sir.
Ma'am, in this example, dependent variable is athletes and non-athletes, and dependent
No, sir,
variable is.
dependent variable is not athletes and not athlete. Dependent variable is time taken to run a mile.
Sorry, sir. Dependent variables are athletes and non-athletes, and
Sir, again, sir, independent variable is athlete and non-athlete.
okay.
Let me make it clear. I'm just writing it. dv is equal to time taken to run a mile. And this time is dependent on what? The independent variable,
Athlete or non-athlete?
the category of category of the student. Category of the student, where student is divided into two groups or categories, athletes and non-athletes. Now is it clear?
Yes, sir.
So this time
Yes,
taken
sir.
to run a mile is dependent, whereas the status or the category of the student is the independent variable, because time taken to run a mile will depend on the category of the student, whether he is an athlete or non-athlete. Am I clear on this?
Yes, sir. Yes, sir.
Now, let's check this. Here is our data set. So some preliminary test. See, these preliminary tests are nothing but ornamental in nature, which gives you the overall insight on the data. Rather than going for directly jumping to the hypothesis test, if you do this preliminary test, you will have two things. First thing is, it will raise the interest in the reader or the audience, that okay, if this is the output, what would be the more outcome that we can infer. Second thing, in country like India, where the research is mostly, if I talk of PhD research, I don't know how many of you will agree with me, where research or PhD research basically is more about thickness of the thesis rather than the quality of the thesis, number of pages. So you can increase your number of pages also. So qualitatively, in research paper, you can give better insights to the reader or the reviewer, be more clear and specific. Whereas in case of PhD research, you can increase the thickness of your PhD thesis. So some preliminary test, which will give you some better analysis and rationale to conduct the further analysis. So first one is the descriptive. So that is the analysis, compare means and means. So what was our dependent list? What was the dependent variable? Time taken to run a mile, isn't it?
Yes, sir.
Yes, sir.
Okay. And what was our category or independent list? The category of the student divided into athlete or non-athlete. Fine.
Yes, sir.
Okay. It will give you interesting result that
So can you repeat the steps, please?
simply you go to analyze, compare means and select means. In that, select your dependent variable and independent variable. However, if it would have been SPSS, it would have also given you a box plot. This PSPP doesn't give a box plot, but through the statistics you can see. You will get, once you click OK, you will get this output. So one insight you can get that in your population, total number of athletes were 226. Total number of non-athletes were 226, whereas total number of athletes were 166. Now, time taken for athletes would be greater, or time taken by non-athletes will be greater?
So non-athlete.
So simply you can say, see, the mean time taken by the athletes is 9 minutes 6 seconds. Non-athletes, sorry. And in time taken by the athletes to run a mile was, the mean time was 6 minutes 51 seconds. However, if you see in standard deviations also, time taken by non-athletes is 2 minutes 1 second, whereas time taken by athletes were only 49 seconds. So you can see this variation that corresponds also to the mean value. Okay, so it will give you a better insight. And there is here this option is not there to make the box plot, but yes, descriptive you can see descriptive statistics explore. Here we don't have the box plot, so simply you just take the table. Factor list is basically your independent variable where it is divided into categories. So let's see, there is nothing called box plot. Extremes you can take, continue. In options, exclude case list wise, always check this because some are missing values. So always check this. Okay. So the highest and the lowest time taken that it will give you. And any other insight it will give you. Yes, the variance you can see in case of this is 13,996, 13,996. The variance is there, but since box plot is not there, so this doesn't make any sense to report this. Only just take that mean value and you can write from there only that is this preliminary test. Yes, here it is given. Now for the athletes, here we have seen that the time taken by non-athletes was 9 minutes 6 seconds and time taken by athletes was 6 minutes 51 seconds with a standard deviation of 2 minutes 1 second for athletes, sorry, non-athletes, and 49 seconds for athletes. The same thing will be resembled in the variance also, the standard deviation. You will see that the variance in case of non-athletes is 13996.57, whereas the variance in case of athletes is 14802.28, or simply you can write 14803. Okay. Yes, in case of non-athletes, this comes to be 244.86. So the variance in case of non-athletes is 14802, whereas variance in case of athletes is 244. So based on all these statistics, you can say that there exists a difference between the athletes and the non-athletes to run a mile distance. Based on the mean value, standard deviation, and variance, you can say that standard deviation, the mean value of the time is also high in non-athletes, the standard deviation is also high, the variance is also high as compared to athletes. So overall, there exists a significant difference, or simply you can say there exists a difference. We'll check the significance later on. There exists a difference, and this difference is like that athletes take less time to run a mile as compared to non-athletes. Now, whether this difference is significant, to check that, simply go to independent t-test, analyze, compare means, independent t-test. So you can write all these things from independent t-test only. P is less than alpha or P is greater than alpha, reject or accept, like that. But to give more meaningful insights, you can also write the results that you have got from mean, standard deviation, because it's ultimately a comparison of means, mean, standard deviations, and all these things. So my test variable was time taken to run a mile, and grouping variable was athlete. Now I will define the group. So group value 1 is 0, non-athletes, and group value 2 is 1, the athletes. Continue. In the options, it's already by default exclude case by case analysis for missing values. 95% confidence interval is there. Leave it is. Click on OK. Now you will get this thing. The same value that you have got earlier. Okay. Now here you have got two p-values. One is the case equal variances assumed and equal variances not assumed. Which one will you take in this case?
So not assumed,
How?
because equal variance assumed, it becomes significant, so null hypothesis will be rejected.
In both the cases, it is significant. See, in both the cases, just look at this. In both the cases, is 0.000 and 0.000. Are you getting this?
Sir, in equal variances not assumed, t value is high and standard error is also low.
This is not the rule. This is not the at all.
So we take equal variance assumed because our
So
length
if we have to do all this guesswork, then why we have gone for framing a hypothesis for the Leibniz test? We already have framed a hypothesis. If you could see. Here we have assumed, here we have taken the variances, equality of variances or not, the two hypotheses. Yes, audience. Here already we have taken a hypothesis for the Leibniz test for equality of variances also. We will check this hypothesis also. Am I clear on this?
sir.
So it's not a guesswork that we will take equal variances assumed or not assumed. First, to check this hypothesis also. For that, go to analyze, go to compare means, go to one-way ANOVA, and take your these two groups. And what was my another group? Grouping variable, athlete. Click homogeneity. Click OK, and see whether homogeneity of variance is met or not. Now P is less than. Are you getting this?
Yes, sir.
P is less than alpha. Null hypothesis. So if you are rejecting, what was your null hypothesis? There was equal variance in the population. Now this hypothesis stands rejected. So we can say that equal variances are not assumed. The population variance of group 1 and group 2 are not equal. Then only we can report, after checking this hypothesis only, we can report whether we have to take the, because there had to be a rationale that whether you want, how come you are taking the equal variances assumed or equal variances not assumed. In our case, the equal variances are not assumed. The null hypothesis was rejected. So which statistic we will take?
So equal variance not assumed.
Of course. So in that case, however significant it is 0.00, but still the statistic will change. There is some equal. Okay. So we will write the report like T at the degree of freedom. Which degree of freedom we will take? Second one, 315.79. to be small t by default. Okay. T15 79. Let me use this notepad, it will be better. So simply you can write here T at the degree of freedom 315. Already you will write that we are taking the equal variances, not assume, because when we have tested the hypothesis of Leibniz test for homogeneity of variance, null hypothesis was rejected, which says that now the variances are not equally distributed. 315.79 is equal to how much? 15.05 at this value, because actually why we have to take this why we have to take this degree of freedom and the t value, because only when you see the table of t, only at this degree of freedom and at this value you will say that p is less than 0.05. P is less than 0.05. So null hypothesis is rejected. And what was our null hypothesis? Null hypothesis was that mu1 is equal to mu2. Means there is no significant difference between the two groups. Now this null hypothesis is rejected, so final result is there exists a significant difference between the two groups. Means there exists a significant difference between the athletes and non-athletes to run a mile. Time taken to run a mile is significantly different between the athletes and non-athletes. And how much that difference is, you have to report that also. Can anybody tell me what is that difference? Anybody who can tell me?
Said the difference.
Yeah. Null hypothesis rejected. Please mute somebody. My wife is equal at somebody. So already it has been established that at the degree of freedom of 315.79, the value of t comes out to be 5.05. At this degree of freedom and at this value of t, the value of p is less than alpha. It's 0.000, less than 0.05. Null hypothesis is rejected. If null hypothesis is rejected, we can say that there exists a difference between athletes and not athletes to run a mile. But how much?
So this 134.79.
No.
Sir,
The mean difference is same between the two.
15.05.
No. Not at all.
So the value of the t statistic.
Sorry?
The value of the t statistic.
Value of the t statistic.
The mean value the population one group.
I don't think so. Somewhere we have calculated a table, a descriptive table.
The mean and
Can you see this? Why we have calculated this? It was some purpose. Now can you tell me something about it? Sir, please mute my voice.
Sir, in comparatively, a non-athlete will take 3 minutes more than an athlete. 6 minutes 51 seconds versus
So
9 minutes.
you can write like this, that there was a significant difference between athletes and non-athletes to run a mile, where the average time taken by the athletes was 2 minutes 55 seconds less as compared to non-athletes. Or non-athletes took 2 minutes 55 seconds more than the athletes to run a mile. So first you have to tell whether there exists a difference or not. Then you have to tell that whether that difference is significant or not. And if that difference is significant, then how much difference is coming. Then only your statistic result will be proper. Is that clear?
Yes, sir.
That's why I have calculated this. I said that this will give you meaningful insights further on. Based on this table only you can see that is, if there, see, you need not report if the difference is insignificant. Since difference is significant, so you can say prima facie it is all these tables tell that there is a significant difference. Further, the independent t test tells you that whether the difference was significant or not. Then based on this table you can say that how much time athlete took and how much time a non-athlete took. So based on this you can say that non-athletes took 2 minutes 55 seconds more than as compared to athletes to run a mile. And this difference stands significant. So it's very childish to write P is less than alpha reject null. This won't serve the purpose. You have to give more insights on your data. Should I move forward?
So means, sir, please, we just it means subtract the mean value.
Sorry? Yeah, you have to see the difference between two means.
Okay, fine.
In case of all the tests, pair t-test, independent test, everywhere you have to take this, because then what is the meaning of this mean? Why, if you are not taking the mean difference, there exists no meaning for that. Okay.
Okay, sir.
Okay. Can I take a 2-minute break? Just, I want some water. Just a 2-minute break.
Yes, sir, definitely.
Thank you. Now moving forward is the pair t-test. This is one of the best statistic to apply basically on the on the longitudinal data or time series data. When you are conducting any longitudinal research, where you are taking one test variable or measuring one variable over a period of time, this is one of the best statistic for time series and other things. Now this pair t-test compare two means that are from the same individual object or related units. And these two means can represent like a measurement taken at two different times, a measurement taken under two different conditions, like a controlled condition and experimental condition on the same individual. So you can see that your groups do not, the characteristic of the group, the basic characteristic of the group does not differ. In previous case, what was the case? That basic characteristic of the group was different from each other. Here, the group, you test them in different at different time points under different situations, but the group characteristic remains the same. Okay, it's like that I said, adding 1 teaspoonful of sugar and 2 teaspoonful of sugar means the characteristic of the sugar remains the same. And you are testing that after adding 1 teaspoon sugar, what is the effect on the taste, how much sweetness is increased, and after 2 teaspoons of sugar, whether the sweetness is increased significantly or not, whether there exists a significant difference between two groups, that is the one group of 1 teaspoonful sugar or 2 teaspoonful sugar or not, or 2 teaspoonful to 3 teaspoonful, like that. Measurement, if taken from two halves or sides of a subject or experimental unit, like measuring hearing loss in a subject's left and right ears, like this, means the uh, group that you are testing, your independent variable, it is divided into two groups where the basic characteristic of the two groups remain the same. What differs is the pre and the post situation, or the normal and the experimental situation, left, right, like this. So the purpose of this test is to determine whether there is statistical evidence that the mean difference between the paired observation, because this will be the case of paired t-test or paired samples. Paired observations on a particular outcome is significantly different from zero, or whether there exists a significant difference between two of the groups where groups are dependent of each other. Dependent of each other means the basic characteristic of the group remains same. So the pair t-test is commonly used to test the following: statistical difference between two time points, statistical difference between two conditions, statistical difference between two measurements, statistical difference between a matched pair, like this. So the data requirements for for the dependent t-test or the pair t-test is that you should have a dependent variable measured on an interval or ratio scale, means it should be metric or continuous. The data should be metric in nature, taken on a continuous scale, that is interval or ratio. The groups that you have created, they should be related or dependent of each other. They should not be mutually exclusive. Sample is taken randomly. Normal distribution, approximate normal distribution should be taken. No outliers. Here there is no case of homogeneity because both the groups are dependent of each other. They are not independent groups. So there is no test for homogeneity. Only you have to test for normality and normal. And this random sample, there shouldn't be any outliers like this. If such situations are not met, then go for the non-parametric equivalent, that is the Wilcoxon test. Now, hypothesis. So the hypothesis in this case could be expressed as same as the independent t-test, same hypothesis. Only difference is there your groups were mutually exclusive of each other. Here the groups are dependent on each other. Means the basic characteristic of the subjects in the group does not change. So the same null hypothesis, mu1 is equal to mu2, alternate mu1 is not equal to mu2, or the paired population means are equal and the paired population means are not equal. Or otherwise, you can write it mu1 minus mu2 is equal to 0, or mu1 minus mu2 is not equal to 0. That is the difference between the paired population means is either equal to 0 or not equal to 0. Where mu1 is the population mean of the variable 1 or the group 1, or mu1 is the population mean of the, sorry, it's not variable 1, it's a group 1. Group 1 and mu2 is the population mean. And both the groups are mutually exclusive of each other. So your data should contain two continuous numeric variables represented in columns that will be used in the analysis. The two variables should represent the pair variables for each subject. And then your data should be arranged differently like that. All these things are there. Now the problem statement. Now sample data set has placement test scores out of 100 points for 4 subject areas: English, reading, math and writing. So let's suppose we are particularly interested in the English and math scores and want to determine whether English or math had higher test scores on average or not. So basically what we want to test here, we want to test that there is one pair of English, one pair of math students, where students are the same, only two related categories, English and math. Whether they have higher test scores on average or not, because their placement test scores have been taken on 100 points. Out of 100 marks, whether the English and the math scores the same or higher or not. So first thing is that you can just go for descriptive statistics. So here we have the data. You can see. So we have the English score and the mathematics score. And then we have, now we want to apply the paired sample t-test in this case. So before, so we can apply here paired t-test to test whether there exists a significant difference in the mean score, mean of the two scores or not, or the two tests, the math and the English. Whether English students score high as compared to math students, or whether the students score high in English as compared to math, or vice versa, or there exists no difference between the scores of the student in English and math. So here, the student is not divided into mutually exclusive group. Only we want to see their scores in English and math. Now, just go for descriptives. Analyze descriptive statistics and go for descriptives. So English and mathematics. Exclude, okay. Exclude entire case if selected variable is missing. Leave it. No, nothing to worry about it. Okay. Somewhere is missing variables are also there. Sorry. So go to analyze descriptive statistics, descriptives. Yes, select include entire case if any selected variable is missing. Yes. Okay. So here you can see 398 students. In English, their score is 82.74%. In math, their average score is 65.45, there exists a huge difference. But whether this difference is statistically significant or not. So for that, you have to check through paired sample t-test. Now this will give you only preliminary information that the minimum score in English was 59.8, maximum was 102. However, this 102 is an outlier if you see. It could not be the case because maximum score is 100 only. Okay. So you can write that there might be some outlier. Then in math, the minimum score was 35.3 and maximum was 93.8. And average was, the mean score was 65.45. Now, whether this difference is statistically significant or not.
Excuse me, sir. Here, valid n and missing n. What is indicate that, sir?
Sorry, sir.
Here, valid n and missing n.
Sir, okay.
So, sir, what they indicate actually? I want to
So
know.
valid n means, see, I had a total sample size of how much?
398.
No, sir. 398 is not the total.
398 plus 37.
Actually, the total was this much. Those data set that were, because I am leaving out the missing variables, so those data set which were found to be valid are only 398. Rest is missing. Are you getting my point?
No, sir.
Sir, we had total number of 435 respondents. See here. Just see here. 435 respondents we have.
Okay.
So sometimes I already told you that some might be missing or some data might not be entered or some might have not, their scores have not been calculated in every case. So we have to exclude those cases.
Okay.
So only those on which the computation was made, they will be written as valid cases. Rest which were missing, they will be written as missing cases.
So, sir, missing case is it technically or by the default?
Sir, missing cases could be, suppose if you are entering the data and the respondent has not responded.
Okay.
Or it could be the case that, let's say, you have failed to enter. Now consider my case. Sir, I have taken test of students in English and mathematics. I had 435 students. I have
Yes, sir.
measured their height, I have measured their weight, I have measured their scores. Let's say 37 students haven't turned in their paper or were absent from the exam.
Yes, sir.
So, but sir, why I have to take all 435? Because in some cases, all 435 had proper response. In let's say here, in one of the case, the student has given the exam, but his weight was not measured. I cannot drop this student. Simply, if I'm measuring if I'm taking weight into account, I will give the command to the software that exclude the missing values. If I'm taking, let's say, scores, I will give the command on that okay, exclude the missing scores.
Okay.
Because if I will include the missing score, then my mean value will be changed a lot. That will affect my mean, because all these that are missing values, that means zero, and that will affect, because if I will take the mean, I will add all these and then divide by 435, I will get a different mean value. So while doing the computation, I have to give instruction to the software that those cases which are missing, you can exclude them.
Okay.
Clear, sir? Now,
Okay, sir.
yesterday I told you that you can read the missing values also by replacing them with the preceding and the succeeding value. Here the case is, sir, it's height, weight, like this. You cannot do like missing or succeeding values. Even if you do, let's say respondent number 7, in some of the case he is missing, in some of the case he has responded, or his response has been taken, or his scores have been taken. So everywhere I cannot, since it's a large data set, I cannot replace the missing values. Neither I can drop this respondent. So what I will do while doing the computation, I will give the software an instruction that those cases which are missing, you exclude them.
Okay.
So what will happen? This will give the reader an insight that, because when you will write your paper or the article or the thesis, you will write that total 435 cases were taken. You will write that. But
Yes, sir.
here, once a person sees that, okay, you have taken only 398 people, then a confusion will arise. To overcome that confusion and to remove that confusion, I have written that I have given the command to remove the missing cases. So this will give that, tell the reader that, okay, 435 respondents were taken, but in this case, in case of this course in English and math, the 37 people have not, their scores have not been taken, so they have been excluded.
Okay, okay.
Clear, sir?
Okay, sir. Fine, fine.
So this will give actually clarity. So now I have seen that there exists a difference, but whether this difference is significant or not. So because the student is the same, only there into two situations I am trying to test. One situation is when they have given their math examination, and one situation when they have given their English examination, where their English and math scores differs or not. On the basis of that, I can tell whether the math ability and the English ability of my students, which one is greater among this, or are they equal. So simply go to analyze, compare means pair t-test. And here, the first variable was English, options, leave it, continue. Take the second variable, mathematics. Right? English, continue. Why it's not taking this? Okay. Variable one in English. Variable two is math. So now I'm making a pair of English and math and testing their scores. Click on OK. Now this table is telling me something. This pair t-test is telling me that P is less than alpha. Null hypothesis is rejected. So null hypothesis rejected tells me that, what are my hypotheses? That mu1 is equal to mu2 situation is not fulfilled. Means this hypothesis is rejected. Null hypothesis is rejected. So it tells that there exists a difference between the math scores and the English scores of the student. So I can write the results like this. Sorry, let me use the notepad itself. T at the degree of freedom. Where is the degree of freedom? 397. T at the degree of freedom 97, 397 comes out to be 36.31. P is less than alpha, reject null hypothesis. It will tell you that there exists a significant difference between the scores of the students when they have given the math exam and when they have given the English exams. Also, it will tell you that English and math scores were having a very weak correlation, which was found to be significant, but their English and math scores were found to be positively correlated, but the correlation was weak. Means it does not say that if a student is good in English, he will be good in maths too. There is a very weak correlation. There exists a correlation. So sometimes students are brilliant. So student is doing good in English also. The student is doing in maths, good in maths also. But we cannot say that those who would do good in English, they will do good in math also. There exists a correlation, but they're very weak correlation. Then there exists a difference also. P is less than alpha. Reject null hypothesis. Now further. So we can say that there exists a scores difference between the scores of the students in English and maths. Now how much difference is there? So simply calculate it from here. Descriptives 82.74 minus 65.45. So overall we can write three results out of this. Number one result, that there exists a significant difference between the students' English and the math scores. The English and math scores are weakly correlated, so it cannot be inferred that if a student is good in English, he will be good in math also. And third thing, that normally or generally on an average, English scores were 17.29 or 17.3 points higher than the math scores at 95% confidence interval. Clear? So null hypothesis is rejected. There exists a significant difference between the student scores if compared with English and maths. If their scores are compared, there exists no correlation. If you write this, it would be better, because sometimes what happens that suppose if one score is higher, another score is also higher, you can say that a student is performing good in English, he can perform good in math also. But through this table, you can say that there is no correlation between their performance in English and math. Both are weakly correlated. There exists a correlation, but weak correlation. It doesn't have much effect. And third thing you can write that on an average, the scores of the students in English was 17.3 points higher than that of their scores in mathematics. Is that clear?
Yes, sir.
Yes, sir.
Now only one thing for today is left, that is ANOVA. If you permit me, then I can cover it, or else we can take it up tomorrow. Depends on you.
Sir, tomorrow, please.
Tomorrow we have correlation, regression, but yes, that's not regression. We don't have chi-square and correlation. Yes, it will be covered. Fine, no issues. So I hope there was some meaningful insight today regarding these three tests. This seems very easy that okay, t-test, there is nothing good big in t-test, but when you start reporting your results, even t-test have a lot of uh, things to report. So
Right, sir.
now for today,
Yes, sir.
I am done.